Hi everyone. Okay, so earlier this week we discussed contact metamorphism of dry country rocks and wet country rocks and what that metamorphism looks like. The second type of contact metamorphism actually involves the release of fluids from the pluton itself. And this kind of metamorphism, known as metasomatism, which is changing the body of the rock, so it changes the composition as well as the mineralogy, it can actually form ore deposits. So it's very, very useful for that reason. Okay, so once again, let's just take a quick look at where we've been. We've previously seen a little rock, Petra, partially melt in the mantle, rise up as a basaltic melt, erupt at the mid-ocean ridge, be metamorphosed as it crossed the seafloor, and then even more so as it got subducted into the mantle, release fluids which then cause melting within the overlying mantle wedge, produce granitoids and which diversify, and a granitoid melt which diversifies as it travels upwards in the crust, and can either erupt at the surface through arc volcanism or can intrude as a granitoid itself. Okay. So today we're going to be back in this environment, the granitoid environment, and we're going to be looking at what happens when granitoids release fluids, so water, carbon dioxide, chlorine, and how that creates ore deposits. Okay, so it's a lovely bornite here. Okay, so let's firstly think about release of hydromagmatic fluids. So we're going to look at two different scenarios here, okay, of plutons. So please bear with me on my dodgy drawing capabilities. This is a pluton, right, in the very classic blob model sense. What we're imagining here is that we've had extensive crystallization ongoing. And at this point, all of this pluton is crystallized, all of this area is crystallized, and only this remaining portion is still melt. Okay. As that melt becomes more and more concentrated, what we will see is that eventually the fluids that are contained within that magma can no longer stay dissolved. So just as we saw when we talked about pegmatites and aplites, these fluids are actually going to be released into the surrounding rock. Okay, and again, these can be things like water, carbon dioxide, CO2. It can be things like H2S, SO2, or even chlorine and fluorine. Okay, so these are just some of our fluids that we see being released from a magma chamber. Okay, so that's our crystallization scenario, right? Our other way of releasing fluids is if we have a magma chamber or a body of magma at depth, and that magma moves upwards, right, through a conduit, a dike, and intrudes perhaps a little higher up, okay, then what we can see is that release of pressure, so that pressure decrease, okay, decreasing pressure, can also cause the release of fluids. All right, so, here we're seeing again, decrease of pressure releases fluids from the magma chamber, okay? And we see this particularly when we're talking about volcanic rocks, right? The magma depressurizes through rising up to the surface, and that causes those volatiles held within the magma to come out of solution. So the best kind of conceptual example for this I can think of is a Coke bottle, right? So imagine you've picked up a nice bottle of Coke sealed from the store, you've disinfected it and everything nowadays, and you decide to release the pressure a little bit. You start taking the lid off, and you see that what previously looked like something completely flat, you couldn't see any bubbles within it. As soon as you start to release that lid by turning it a little bit, you will immediately see bubbles starting to form because you've decreased that pressure. The CO2 within that Coke can no longer stay dissolved, and instead it's released as bubbles. This is the same kind of scenario, but here we're talking about a wider variety of volatiles than just CO2. Okay, that's where we're at. So how do we know Well, it turns out that tiny pieces of these fluids can actually be trapped in minerals as the minerals are growing. So these are called fluid inclusions, and they actually give us a snapshot of the fluid conditions at the time that that mineral crystallized. So they're really, really valuable. So if we can analyze these fluid inclusions throughout a deposit or throughout a pluton, we're actually able to, with that compilation of data, understand the evolution of the fluid system over time. Okay, so what you can see here are a variety of different fluid inclusions. In this figure, you can see what they actually look like. They just look like kind of tiny little bubbles within a slide. So this is under the microscope. If we zoom in significantly further, we can see that some of them are filled totally with liquid. We haven't really got any of those examples in here. Some of them are liquid with vapor. So here's a little bubble of vapor here, or here we have a CO2 liquid and a CO2 vapor bubble as well. And some of them actually have crystals in them as well. So here we have a vapor bubble, there's liquid filling this gap, and then there's several solids, right? Several crystals that have crystallized out of here. So these are really useful because if we heat them up on a special type of microscope stage, we're able to figure out the minimum temperature at which that crystal is growing. So it gives us some sort of a constraint on the temperature that those minerals are forming. We can also use a different type of stage, which can measure pressure of the same thing. So with enough fluid inclusions and clear enough fluid inclusions and the right type of microscope, we're actually able to tell the pressure and temperature at which these things were trapped. Okay, and they do this by homogenizing the phases held within that fluid inclusion. So they would heat and pressurize this until it all became homogeneous, one fluid-filled bubble. Okay, and the rationale here is it's much more likely that this was trapped as one phase, as opposed to it happened to collect multiple small crystals and some fluid and a vapor at the same time. Okay, so that's how we can figure that out. So fluid inclusions are really, really useful because they can tell us a lot about the conditions of the fluids that were present in the rock at the time that the rock formed. Okay. So in addition to our magmatic fluids that we've just talked about, the hydromagmatic fluids, the ones that were released from a pluton, we can also get different types of fluids involved in metasomatism, so in metamorphosing pre-existing rocks. And this can be meteoric water, so groundwater, or it can also include metamorphic waters. So these are the fluids that are released by the metamorphic breakdown of hydrous minerals. Okay, so when we heat up our micas, for example, we know that at a certain temperature, the micas destabilize, they break down into other minerals, and they release a fluid. And that's one of the things that causes melting in subduction zones, right? Is the breakdown of those micas as the rocks are subducted, the basaltic crust is subducted deeper into the mantle. Those fluids then, the metamorphic fluids, are then released into the overlying lithosphere, lithospheric mantle, which then partially melts. Okay, so these fluids can also cause metasomatism within the crust as well. All right, so the most famous types of metasomatic deposits are ore deposits. So we're going to talk about a couple of different types of ore deposit today. All right, so the first one we're going to talk about is porphyry deposits. And what you can see on this map is the red circles and the distribution of porphyry deposits around the world. Okay, so porphyries are really, really important. They are the largest global source of copper and molybdenum. They are also a very significant source of gold. So they're really important for our economic minerals, some of our metals. They are usually very large deposits, so they tend to have hundreds of millions to billions of tons of ore, right, which is our economic rock, but they tend to be relatively low grade. So for example, in our copper deposits, we tend to see grades of only, concentrations of only about 0.5 to 1.5% copper, which is relatively dilute, if you will, right? Low concentrations of the ore mineral. Our metals in these deposits are typically found as sulfides. So here are some of the sulfides that are commonly found in porphyry deposits. These are our copper sulfides like bornite, chalcocite, chalcopyrite. We might also see molybdenite, which is our major molybdenum sulfide. We might also see some tungstates, so things like scheelite and wolframite, okay, are tungsten-bearing deposits. Okay, so moving forward, why are we talking about these now? These porphyry deposits are hydromagmatic deposits, okay, so they tend to be related to relatively small volume, calc-alkaline to alkaline, intermediate intrusions or felsic intrusions with a porphyritic texture. Okay, so the fact that I said calc-alkaline should tell you immediately that we are in a volcanic arc setting, because remember, we only find calc-alkaline rocks in our subduction settings. We know that there are typically two fluids involved in formation of porphyries. One of them is released from a pluton and causes most of the ore deposition, the metal deposition. And the other one is typically a meteoric fluid, a groundwater, that mixes with that magmatic fluid and can cause kind of lower grade alteration on the margins of this deposit region. Okay, these tend to have a very typical alteration and mineralization pattern. They tend to be very, very rich in pyrite, as well as our other sulfides, often chalcopyrite and bornite as well. And the ore tends to be found in veins, as well as disseminated throughout the rock. So it can be as kind of fractures that have been infilled with sulfides, or it can be as random sort of blobs of sulfide throughout the rock, wherever the fluid has pervasively infiltrated through the entire rock region. Okay, so let's think about a possible mechanism for the formation of our porphyry deposits. What we're seeing here, let's see, is, oh dear, sorry, I did something weird. Okay, so what we're seeing here is our intrusion of a magma. So this is our magmatic body around here that I'm just highlighting very badly. So we can see intrusion of a magma. We can then see it tends to rise to high levels in the crust. So we tend to get relatively shallow depths before crystallization happens. This means that our fluids tend to be exsolving from the magma because of this loss of pressure. Okay, these fluids are then going to be released into the surrounding rock, and you can see that here this is occurring. We're now looking at our magma body here, which is altering itself. Okay, so these fluids are actually being released from the magma here, and they are moving upwards, and they are altering firstly the pre-existing magma, or the pre-existing rock, magmatic rock that is just crystallized from the same intrusion, but they're also going to be altering the surrounding rock as well. Okay, so we find this ore shell is what we're seeing in this region here. Okay, we're also seeing a porphyry, which is a porphyritic textured dike, which is kind of acting as a conduit for those fluids in this region. And then we see that any fluids that make it to the surface, this is meant to be a volcano, we get this advanced argillic alteration, which is kind of clay alteration. This is like you see at Bumpus Hell at Lassen. Okay, so this kind of very clay rock type giving off sulfurous gases at the surface and lots of strong rotten egg smell. All right, so this is, as the system develops further, we see, again, development of different types of alteration. So here you can see some of the different types of alteration listed, and we're not going to talk about these today, but if you guys get a chance to take an economic geology class, I would highly recommend it, partly because I teach it, but it's worth taking if you're interested in learning more about ore deposits. Okay. Typically, we see that we have multiple influxes of magma from below Some of these may be mafic, which would contribute different elements, maybe more sulfur than our felsic melts typically would. But this constant kind of influx of magma is going to cause potential eruptions, but it's also going to release more and more fluids, causing kind of alteration and then re-alteration of the same region. Okay, lots of kind of overlapping alteration phases. All right, so that's what we see there. I'm going to stop this and then I'll come back and talk about skarn deposits in a minute.